Can you upload the PowerPoint slide for the introduction? So please upload the PowerPoint slide for the introduction. Okay. So people are coming in, so we'll wait a couple more minutes before we start. Okay. Okay, good afternoon. My name is Haesung Kang, one of the vice president of the IAU. Okay, fast radio bursts are intense bursts of radio emission lasting only a few milliseconds, and their exact origins remain one of the greatest mysteries in astronomy. In a seminal paper published in Science in 2007, Duncan Lorimer, Matthew Bales, and Maura McLaughlin and their collaborators reported the first discovery of FRBs. In recognition of their pioneering work, the Shaw Prize in Astronomy was awarded in 2023 in equal shares to Matthew Bales and Duncan Lorimer and Maura McLaughlin for their discovery of FRBs. Professor Matthew Bales graduated from the Australian National University with a PhD in 1990, focusing on the origin of pulsar velocities under the supervision of Dick Manchester. As a postdoctoral fellow, he worked with Andrew Lin on Park's millisecond pulsar surveys, collaborating with his first graduate student, Duncan Lorimer, at the University of Manchester and C. Cyril. After the discovery of the Lorimer burst, he played a crucial role in developing the digital receiver system that revealed the cosmological population of fast radio bursts as part of the high time resolution universe collaboration. Today, he leads the Australian Research Council Centre of Excellence for Gravitational Wave Discovery at Swinburne University of Technology. Next, we have Professor Duncan Lorimer. After graduating from Cardiff University in 1990 with a BSc in astrophysics, Duncan pursued his master's and PhD degrees at the University of Manchester, working with Andrew Lin, Dick Manchester, and Matthew Bales. Before joining the faculty at West Virginia University in 2006, he held postdoctoral positions at the Max Planck Institute for Radio Astronomy in Bonn, the Arecibo Observatory, and the University of Manchester. Duncan's research focused on the search for and understanding of neutron stars' population and evolution, leading naturally to his role in the discovery of FRBs. Currently, he is dedicated to understanding the various populations of FRBs. Finally, Professor Maura McLaughlin received her PhD from Cornell University in the USA. She then became a postdoctoral research associate at the Jodrell Bank Observatory in the UK, and is now a professor and the chair of Department of Physics and Astronomy at West Virginia University. She is a leading expert in studying transient radio sources such as pulsars and FRBs, and served as a co-director of the Nanograv Physics Frontiers Center. Along with partners in the International Pulsar Timing Array collaboration, she announced the first evidence for a background of low-frequency gravitational waves last year. Additionally, she is passionate about outreach and education, having involved thousands of high school students in pulsar searches through the Pulsar Science Collaboratory since 2008. So now, please join me in welcoming our first speaker, Professor Duncan Lorimer, with a big round of applause.
Thank you so much for that lovely introduction. It's a real pleasure to be here in South Africa to give this talk today, and we're really looking forward to telling the story about fast radio bursts. Can get this to work. So, as this is a radio astronomy focused endeavor, I thought it was appropriate, and given that we're here in Cape Town, to begin with a recent picture of the radio sky that was taken with the Meerkat telescope here in South Africa. So this is an image showing the radio sky in around 20 centimeter wavelength, focused in on the central regions of our Milky Way. So you can see a very dynamic, turbulent environment with the bright spot there at the center, that's Sagittarius A star, where the supermassive black hole lives at the center of the galaxy, and this filamentary structures that are indicative of a highly magnetized environment. And you can see these shell-like features, these supernova remnants, in many cases, that point to the origins of neutron stars in the central regions of the galaxies that were formed by supernova explosions. Zooming out a little bit to 5 centimeter wavelength, got to click in the right direction. Maybe I have to point it there. Oh, there we go. All right. So if we go out to 5 centimeter wavelength, this is our backyard where Maura and I live in West Virginia. This is the West Virginia premier observatory in West Virginia at the Green Bank Observatory. And so you can see the skyline there in the background, but the sky itself, that's the sky at 5 centimeter radio waves, and showing, again, radio continuum at that wavelength. And so that was made with the now defunct 300-foot telescope at Green Bank. But what you can see there is in the image are points of light, radio light. And rather than being each point being a star like we would expect when we look out with our eyes, these are actually external galaxies, predominantly. You can see those extended features there that are similar to the ones we saw in the center of the Milky Way, supernova remnants and other features in the Milky Way that are emitting radio waves. But predominantly you have those external galaxies. And the key point that we're trying to make here at the beginning is that radio is providing a complementary picture, this multi-wavelength view of the universe. They're revealing things in our universe that we otherwise wouldn't have seen, and fast radio bursts are a great example of that. So the fast radio bursts themselves turn out to be this cosmological population coming from, in some cases, the galaxies that we're looking at here. They're typically going off at random intervals in the sky every few seconds. And I think, if I can get this next one to work, what you're listening to there is the background radio noise, and then on top you're hearing the fast radio burst. This is a simulation. I'll let them play for a few seconds. There's one. And so there are different durations and intensities, but that's roughly speaking somewhere on the sky at about that cadence they're going off. So our observations revealed this remarkable phenomenon that we now understand today as fast radio bursts. And what you heard in the audio recording there was a chirp. And so that's trying to depict what's happening at the telescope, where the highest frequency radio waves arrive first compared to the low frequency components. And so you can see that on the plot there on the left, which is showing frequency versus time. And the pulse, that was the original one that we found, which is now known as the Lorimer burst, you can see has that characteristic frequency sweep there, which is due to the propagation of the radio signal through an ionized plasma. This is a very familiar situation to plasma physicists, but also to pulsar astronomers, who've been using this phenomenon for years to measure the dispersion of radio signals in the Milky Way. But what we're now using it to see is the presence of free electrons out along the universe as well. In that schematic in the top right, you can see the presence of those free electrons essentially introduces a frequency-dependent refractive index and causes the lower frequency waves to arrive later. Those two equations down there characterize the astrophysical nature of the signal. So what we call DM, in this case it's dispersion measure, not dark matter. So what we call DM is the integrated column density of free electrons along the line of sight. So that's the astrophysical quantity. The bottom equation shows the time delay that you're seeing in the data there. And in that particular case, from top to bottom, there's about a 300 millisecond delay. And you can measure that time delay, and you can infer the DM from that. And so you get information about the electron content along the line of sight. So that's a very important quantity that we'll come back to throughout the talk. One of the things that's attracted me to radio astronomy, perhaps my colleagues as well, is just the wonder of these radio telescopes, these gigantic pieces of metal that swirl around and collect radiation from the sky. And here is one that played a role in this discovery and found the original fast radio burst, as was mentioned in the introduction, where I spent a good bit of my time. It's the Parkes Radio Telescope in New South Wales, Australia, now known as Murayang. And it's a 64-meter dish, and crucially, over 25 years ago now, actually almost 30 years ago, there was a 13-beam camera that was hoisted into the focus of the receiver, where the radio waves come to a focus. That allows the telescope to look at 13 positions at once, and it kind of really accelerated the process of discovery for this telescope, and there have been similar systems since then. So you have this sort of footprint on the sky of positions that you're looking at. Now, to understand fast radio bursts, we need to go back a little bit into the past, into the late 60s now, and look at another kind of radio telescope. This one is an array of dipoles at the University of Cambridge. that is strewn across a field in the fens there, and it's essentially an FM radio telescope working in the FM band, so at hundreds of megahertz frequency. In this case, the telescope was designed to look for interplanetary scintillation of radio waves from distant quasars, rather like the optical twinkling of stars by the Earth's atmosphere. For quasars, you have the interplanetary medium produces a radio wave twinkling, which they were studying. That telescope led to this unexpected discovery in the time domain, and this is the well-known story of the discovery of pulsars by Jocelyn Bell Burnell, who was working in that group and diligently found these time-variable radio pulsations in the data, unlike which no one had ever seen before. In this case, what you're looking at in the lobe trace there are pulses that are spaced by just over a second apart. And these are now understood to be coming from rotating neutron stars where the magnetic field sweeps past your line of sight once per rotation. That's a wonderful story. I'm sure many of you are aware of it, but it's a great example of serendipity in astronomy and science in general, and has led to many breakthroughs over the years, and people like us have spent all our scientific lives studying pulsars. And one of the great discoveries early on, 1968, was made actually at Green Bank, shortly after Jocelyn's discovery, really made the connection between rotating neutron stars and pulsars, was the discovery of giant pulses coming from the Crab Nebula, the famous remnant of the supernova explosion of 1054 AD that you're looking at there. And superposed on that image are radio pulses coming from that nebula that was so bright they could be seen individually with even small telescopes. But this discovery really highlighted the fact that it not only made the connection with pulsars and supernova remnants and rotating neutron stars, but it also had a great prediction that we could see these sources to distances well beyond the Milky Way. So people started realizing that you could detect radio waves at great distances, perhaps by detecting systems such as this one well beyond the Milky Way. So what led to the discovery of fast radio bursts really began around that time in the early 70s through to the early 2000s. This slide is trying to capture 30 years of searching for transient radio pulses from external galaxies. I won't run through all the details here, but some of the theoretical predictions were made fairly early on about types of sources that could produce these dispersed pulses. Some of the early searches were carried out by John Jelly, shown there. And then, thanks to theoretical work, pointing to other types of sources, the community was energized to look for black hole explosions predicted by Stephen Hawking. So Still Finney, shown there, and Joe Taylor were among the first to carry out searches for those types of events. Nothing was really found. There was a hint of a discovery in the early 80s from Linscott and Erks, which of dispersed pulses from M87 that were never confirmed. And really the field went quiet for a while until the early 2000s, when our co-laureate Hiyamura was working then as a PhD student in Jim Cordes' lab, and they were really pioneering ways to more systematically look for these pulses. And so one of the things that Maura developed with her PhD was a single pulse pipeline. And so in effect, we took the data from these radio telescopes and corrected for this dispersion effect over a wide range of DM values and searched each of the individual so-called de-dispersed time series for statistically significant pulses. And you can see the result of that analysis there as dispersion measure versus time. And the background noise that you were listening to in that audio file are those little white dots there of just sort of random noise pulses. But then the individual pulses, in this case from a known source, can be seen as those dark symbols there at non-zero dispersion measures. You know, the key aspect, if you've not thought about this before, is think of dispersion measure as a proxy for distance. So increasing dispersion measure means increasing distance. So that discovery led to, as shown on the title of that paper at the top there, to a new kind of way of finding pulsars in our galaxy just through individual pulses rather than long streams of periodic signals. We were now able to see them through their individual pulses in a very systematic way, thanks to Maura's pioneering work. And so that led us to the discovery of fast radio bursts, which began about 18 years ago when Maura and I moved to West Virginia. And they're pictured where we are pictured back in the day, before we knew how to hold babies properly. But we quickly figured that out. And our son now is taller than we are, and he's off to college himself. But back then we were new professors and very excited to be working with undergraduate students and just getting started on new projects. So the quickest way to do that is to grab some data that already existed. And so we were aware of many different data sets, and we had these powerful techniques that I just outlined to find individual pulses. And one of the data sets that we were really interested in looking at was pulsar surveys of the Magellanic Clouds using that Parkes multibeam system that was just mentioned. And the data already existed, and so we were able to get a copy of it and begin to search the data in the way that I just outlined. And so what we were really trying to find was individual pulses from sources in the Magellanic Clouds that had previously been missed by regular searches for pulsars. And so there's a picture of me and Ash Narkovic, the undergraduate student who ultimately made the discovery of the first source. And here is a picture of one of the outputs from the data analysis pipeline. So again, you've got dispersion measure versus time. So think of it as distance versus time. Thank you. This is a picture of the basically a test observation. It's a known pulsar in the Large Magellanic Cloud. But you can see that observation there is a couple of hours in duration there. And you can see multiple individual pulses that were detected by the pipeline. So we had this all up and running, and we were able to get into a rhythm, and Ash would come to my office every week and we'd review the latest progress. And then one day they turned up in the office and showed me this. So it's dispersion measure against time there on the right-hand side. And you can see this huge event here, this very large symbol that indicates a very high signal-to-noise, just individual pulse at a very large dispersion measure. So we got very excited about this and sort of tried to figure out where it was in the survey region. It actually turned out to be south of the small Magellanic Cloud, in kind of an additional set of pointings that we got covering a slightly larger region of sky. Our collaborator Frony Crawford, shown here, made this map that shows the positions of the pulsars and their dispersion measures. So those numbers in parentheses there, 76, 70, 105, are the dispersion measures you would expect for the Magellanic Cloud. And here's our footprint from the Parkes multibeam receiver. And you can see the pulsar, the burst was detected in these symbols down, these beams down in the bottom here, and localized to a couple of degrees south of the Large Magellanic Cloud. So we had this incredibly bright event with a very large dispersion measure that seemed to be just looking in a sightline through the universe. And so here's the picture that I want you to have in your mind's eye throughout the rest of this talk. where this really large dispersion measure, much larger than we'd have expected from the Milky Way, we weren't looking through any of the Magellanic Cloud. What we're really seeing here are different dispersion measure contributions. So we're getting dispersion measure from the host galaxy, we're getting dispersion measure potentially from an environment within close to the source, and then the intergalactic medium has free electrons in it, perhaps piercing galaxies along the way until the pulse reaches the Milky Way. And so you can see a timeline of the pulse as it traversed the universe to get to us. In this case, the pulse arrived on July 24th, 2001. And these are little frequency versus time shots showing the pulse as it was emitted from the source, and then gradually getting more and more dispersed as it traveled through the universe to us. And that process takes about 3 billion years. So we made some estimates from the dispersion measure that the pulse was about 3 billion light years away. So we had this very bright event. Not only was it bright apparently, but it was intrinsically very luminous. And it was a very brief event. When we measured the width of the pulse, it was only a few milliseconds in duration. So this diagram kind of puts it into context here. What was now being called the Lorimer burst had this, when you plot its luminosity versus essentially the width of the pulse and compare it to the known pulsars, it's orders of magnitude above that. And even the brightest giant pulses from the crab, it's much more luminous than that. So we're essentially looking at a new class of object here where it's putting out a solar luminosity about as much energy as the sun puts out in a month. It's putting out in a few milliseconds. So what could it be? We were obviously inspired by our origins studying neutron stars. We knew that neutron stars can produce bright pulses. We also knew that the width was very short, so it was a short duration pulse. And so from light travel time arguments, you're looking at compact regions. So compact objects are a very good clue to that and have a large energy source. But it was by no means clear to us. There were a number of options, but it was something to do with a neutron star or perhaps a white dwarf that was producing this energetic event. And it seemed at that time to just be a one-off pulse, although the story gets a bit more complicated, as we'll see. I'm going to end my portion of the talk with just a slightly more humorous note of thinking about how this burst, this Lorimer burst, has kind of entered the zeitgeist of popular culture. It turns out that there is a German post-instrumental rock band that you can find online that are named after us. They have an album out called Dispersion that you might want to check out. And I found them when I was Googling for a talk one night, and so that was quite interesting. They also feature in this book about relationships as well that you can find too. So it's been that's been an interesting side story that this pulse has made. But more importantly, as I transition now to Matthew, we're going to look at the implications of this pulse and what it means. So I'll turn it over to Matthew.
Yeah, thanks very much, Dunk. My entrance into this story was when I was actually at the Parkes telescope with Duncan on a somewhat ill-fated 6 gigahertz pulsar survey that I believe Dunk had done the simulations for, which had predicted a large number of pulsars were going to flow. Sadly, the prediction didn't prove as successful as the Lorimer burst discovery, and we didn't have a lot to do. And I asked him at one point if he'd found anything interesting lately. And he asked me, have you ever found, a pulsar with Parkes that appears in more than one beam in the discovery? And there's a very famous millisecond pulsar called 1909 minus 3744, which is part of most of the pulsar timing arrays in the world. And it's quite a bright pulsar, and I remembered that Brian Jacobi, when he discovered that, had found it in 3 beams of the Parkes multi-beam. And so I said, yes, I have, and he had the nice diagnostic plot that Maura had put together with the big circles. And we just got chatting about this, and we eventually made the waterfall plot, which is now kind of famous over here, showing the dispersion. And I remember when that came up on the screen, we were just completely shocked, and Duncan had a lovely reaction to it. He just started laughing with a characteristic Lorimer chuckle, because it just looked too good to be true. There was this insanely bright burst sweeping through the Parkes telescope, and this is a nice story of the genealogy of discovery. This survey was actually originally headed by my old PhD advisor, Dick Manchester, and the data had sat on shelves for about 5 or 6 years and not been looked at for single pulses. With Maura's discovery of the rats, which were these single pulse emitting neutron stars, everybody was grabbing archival surveys and looking for more. And Duncan had the vision to look at the Magellanic Cloud data with Ash and Maura. And, you know, hidden in that was this remarkable sweep. And had been seen in two of the 13 beams, but not in the others. And we couldn't quite work out why it didn't pop up in a third beam. And it turned out that Andrew Lyne, who was a former supervisor / advisor to us both, had written a very clever algorithm that could spot interference. And it looked at the statistics of 1 second blocks of data. And if they weren't Gaussian, Andrew had decided it must be interference. And so it actually deleted the burst in its most prominent beam. So we actually did our very best to delete the Lorimer burst, and if it had only been a single pixel receiver, we wouldn't be standing here today. Fortunately, there's things called in side lobes in radio astronomy, and we ended up with this beautiful sweep, which enabled us to localize the source more accurately. And I remember being very excited by this, and I had no knowledge of the intergalactic medium, being a pulsar astronomer. And I didn't realize there was only 1 electron per cubic meter. And when we first calculated that, put the thing at about 1 gigaparsec. And the observatory beds at Parkes were not the best to sleep in at any time, but with these thoughts running through my head that this might be a brand new type of event, I really couldn't sleep that night, just thinking about the ramifications of this, what eventually became known as a fast radio burst. So this was its luminosity, and often in science, if there's an existing population of things, you don't find things 12 orders of magnitude more bright. So whilst it was a very exciting potential event, the bottom line was that hundreds of similar events should be possible to be discovered. And indeed, when we submitted this paper originally to Nature, it got rejected. And one of the reasons for the rejection, without going to referees, was that, how come you can't find more? And so in the back of my mind was, is this one of the great discoveries of astronomy, or is this some form of interference or misinterpretation of the data? And that became a great cause of concern. So, of course, we decided to look for more bursts. I travelled back up to Parkes and got in the telescope and pointed it at the direction of the Lorimer burst for 90 hours. And I wasn't sure if I was secretly hoping not to discover it, because I wanted it to be like a neutron star merger or something really exotic, or whether to see more. And we didn't see anything. Nobody could find any other examples in other archival surveys that were lying around in the disk. There were some hastily put together new surveys specifically to look for fast radio bursts. I think Andrew Simeon, who's of SETI fame, took the Allen array and pointed it in lots of different directions. And there was the nagging doubt, at least in my head, that maybe the Lorimer burst was too good to be true. But it was still worth publishing in Science. And then one day when I was at Berkeley, my new student, Sarah Birks-Ballore, who'd been asked to find fast radio bursts in other surveys, contacted me and said, "I found another Lorimer burst." And I thought, this is fantastic. and I asked her what the dispersion measure was, and it was almost exactly the same as the Lorimer burst. And she said, and it's in all 13 beams. I thought, I'm not sure that's good news, Sarah, because if something's in all 13 beams, it's in the near field, and it's not a gigaparsec away, it's probably a few hundred meters away. And so Sarah dubbed these things perytons, which I believe is some sort of Greek mythological creature of unknown origin. But when you looked at the dispersion sweep, it didn't look as good, as high quality as the true Lorimer burst. It had these kind of blotches, but it did have a dispersed sweep. So this was a little bit of a concern for me, and doubts were sort of sweeping back to when I once thought I'd discovered the first planet in the solar system going around a pulsar, and it had dissolved in a great retraction in nature, which put my career back a little bit. And I thought, maybe I'm not really cut out for this astronomy thing. And so here's some examples of perytons, and you can see they're not as high quality as Dunk. Some of them have these little funny kinks in them. They're very blotchy. But they are in all 13 beams of the Parkes telescope, so obviously something in the near field. And the late theorist Marquardt thought that maybe they were caused by lightning, and so he actually wrote another Nature paper, which again, unfortunately, was rejected. And we explained that there were these things and people needed to understand them. Evan Keane, who was one of my old postdocs, just before he arrived at Swinburne, found something which we called the Keane burst, and every burst used to have a name. And this was in the archival survey of the galactic plane carried out by the Parkes multi-beam collaboration, which doubled the pulsar population. And it's a pretty good burst. It actually has a nice dispersion sweep. Unfortunately, it was right in the galactic plane, and the dispersion measure models are sufficiently uncertain that it wasn't quite clear whether it was another version of the Lorimer burst or whether it was just some source in the galaxy. But in retrospect, I think it probably was. And my colleagues and I decided that we should do what all great pulsar astronomers do, another survey with the Parkes telescope. But instead of using ye old analog filter banks that Andrew Lyne had devised, which are these magnificent 1-bit systems with 3 megahertz channels, we would do it in a more modern way using digital FPGA technologies. And Dan Wertheimer explained to me how they worked, and we built a new digital system for the Parkes telescope, and we aimed to look at the whole sky, searching for not only Lorimer bursts, but things like millisecond pulsars. And the advantage of these systems were they were digitally precise, so all your filter channels were truly well separated. We had more bits of data, and we had a lot less smearing, so any dispersed pulse would be a lot narrower. And Dan Thornton, who was a graduate student at the University of Manchester, was assigned to do the Lorimer burst searching, and he discovered that interference had got a lot worse over the years, and he was a little bit demoralised. And Ben Stappers, his advisor, said, just set a really high threshold and see what you think, or see what you find. And indeed, he did discover a 50 sigma kind of Lorimer burst, and within a very short period of time, it's amazing what a graduate student discovery can do for motivation, he'd found another 3. And we wrote this paper on the discovery of a population of fast radio bursts at cosmological distances. The name fast radio burst was debated in our collaboration, but I thought the acronym FRB was a little bit like GRB, and I knew everybody did GRBs, and if we had FRBs, it was probably more likely to gain people's attention. So that's how the FRB name came apart. And these, fortunately, didn't have the same dispersion measure as the Lorimer burst. They were distributed, although some number guy discovered that the most intense one was like 3.5 times or 2.5 times the DM of the first one. But it did look magnificent. So I was at Greenbank when I got the email with this waterfall plot, and afterwards maybe if you come up on stage you can look, and it's a beautiful 1 upon nu squared. And the burst got fatter as it got to lower frequencies, which is what you expect for interstellar scattering. And there were these other bursts which fortunately were filling out the log n, log s doubts that were in my mind. So these look very good. This dispersion of 995 parsecs per centimetre cubed placed this thing at about a redshift of 1. And so there was great cause for celebration. When you look at the galactic latitude and the dispersion measure, the blue dots are pulsars either in the galactic plane or the Magellanic Clouds here. This was the Lorimer burst, and then these green dots were the Thornton bursts, and you can see that they were clearly not in our galaxy. I was delighted when Laura Spittler, who's now at the Max Planck Institute, but I think she was a Cornell student at the time, discovered the first burst outside of the Parkes Observatory, 121102, and you'll hear a little bit more about this one later from Moira. But it again had a very high dispersion measure, and it showed that you could discover these things outside of the Parkes Observatory, which was a great relief to me. John Sarkissian, one of the observatory stalwarts of the Parkes Observatory, was enlisted to help us find the origin of the perytons, and microwave ovens were one of the key sort of suspects. And Emily Petroff, who's now at Perimeter for her PhD, realized that these bursts were predominantly occurring at lunchtime. And this was a bit of a giveaway that something that you operated at lunchtime was potentially the cause of the perytons. And they were tracked down to this microwave oven, which for some reason is a billiard cue is being used to open it. It turns out if you open a microwave oven while it's on, it actually gives off an FRB impersonator. So it was very good to be able to put those to bed. So there were more bursts found, this time at the GBT by Masu et al. And then at Parkes we found another 5 in the high time resolution surveys, including 121002, not to be confused with 121102, which seemed to have a double pulse structure. So people were starting to find fast radio bursts all over the sky, and I really started believing that they were true and breathed a great sigh of relief. I'm now going to introduce Moira, who's going to talk to one of the discoveries she was involved with, which really was pivotal in establishing that fast radio bursts were cosmological.
Hey everybody, thank you Matthew. So I was part of this P-alpha, this multi-beam survey with Arecibo that discovered this 121102 burst that Matthew mentioned. And as with all FRBs, we went back to the telescope and we sat on the position of this source, seeing if we could detect any more bursts. And honestly, we really didn't think we would, because all of these other fast radio bursts had many, many hours of reobservation and never a repeated pulse. And lo and behold, though, one day, it was in November 2015, a graduate student named Paul Schultz, who was working at McGill, sent an email out, and the title of the email was "A Minor Point of Interest." And so I remember opening this email like, yeah, okay, well, what's this going to be about? And in the email, he said he had detected several more bursts from the position and at the same dispersion measure of this Arecibo burst. This was super exciting, very unexpected. I looked back at the email chain this morning to refresh myself of the date, and there were, 100 emails in this chain over a span of 12 hours or so, as you might imagine. And so this was really important for a couple reasons. The first reason was this shows all of the different bursts that we published in the first paper about this repeater. Here's the original one. Here are the 10 subsequent ones. They all look different, right? They're all from the same source. These, again, are frequency versus time. The dispersive sweep has been removed, so they're straight. But you can see they have very different spectra. Some are bright in the top part of the band. Some are brighter in the bottom part of the band. Some of them have 2 components. Some of them have a single component, different widths. So this was really interesting. This wasn't too surprising to us. Pulsar single pulses can kind of do this. They can have different shapes, but the sort of spectral differences were a little bit unusual and different from pulsars. The other reason, of course, that this was really important is that there were lots of different mechanisms for FRBs being bandied around, and some of them involved cataclysmic scenarios, right? So a collision of two neutron stars or a supernova explosion. And of course, if this thing repeats, it can't be from a cataclysmic source. It needs to be from something more like a neutron star, or maybe something else that could repeat that we hadn't thought of yet. Okay. The other reason this repeater was really important is that because we knew there was something there, we could go and sit on it with an interferometer and dedicate time to imaging it to get a much better localization. All of the bursts up until this point were detected with single-dish telescopes. So they had arc minutes or even tens of arc minutes localizations, which is not good enough to tell where they're coming from, what galaxy, for instance. So with this 121102, we observed it with the Very Large Array in New Mexico. And this shows that, oops, I didn't mean to do that. This shows the VLA image. These two circles here are the position error circles from the two beams of the Arecibo survey in which this fast radio burst was detected. And here you can see the VLA localization in this little box here. So we went from arc minutes to arc second localization of this FRB, which was super exciting. We also detected an optical counterpart. So we had this radio source here, an optical counterpart. This plot here shows the flux density of what we call this persistent radio source. And you can see the flux varies fairly dramatically with time. These are times of FRB detections. It wasn't real clear what this is. It could be an AGN. It could be some kind of pleryon. But further follow-up observations led to the identification of a galaxy host for this burst. So this was a really important step forward in our understanding of FRBs because, of course, with an optical identification of the galaxy, we could measure a redshift. And the redshift for this particular burst was about 0.2. So this burst came from about 2 billion light years away. And so this was the first proof that these were indeed cosmological. For sure, these bursts were not from some weird phenomenon in our galaxy or a local galaxy. They're coming from very, very far away. It was a weird galaxy. It's a dwarf galaxy, a very low mass galaxy with low metallicity and a high star formation rate. And it turned out this persistent radio source that we detected was offset from the galaxy's center. So not an AGN at the core of this galaxy, but some offset source. Now it seems likely that it's more of a pleryon or remnant instead of an AGN. And all of these are consistent with a young neutron star origin for the burst, right? It's coming from a star-forming galaxy, offset from the center with this persistent radio source around it. A little bit later, we also measured polarization properties of the burst and found it had a very large rotation measure, which means it's coming from a very high magnetic field environment, which is also consistent with a young neutron star. So shortly after this time, the picture got a little more deep. This is work that Matthew did. I think these are pulses from the Malangolo telescope. Matthew worked very hard with his collaborators to develop new backends that could coherently de-disperse the data from that telescope. And this means remove dispersion delays exactly. So instead of this filter bank style of data taking where you have discrete frequency channels, you can remove those delays for a repeating source where you know the DM a priori and resolve much finer scale structure. And here's a picture of two of those bursts. This axis here is milliseconds, so this whole thing is 4 milliseconds. And you can see lots of very fine scale sub-millisecond structure, both in this burst and this other burst. So this was very interesting. This looks a lot like crab giant pulses or some pulsar single pulses. So this, again, was kind of reminiscent of a neutron star pulsar-ish origin for the burst. And in 2019, FRB science changed pretty dramatically. I'm guessing if you haven't heard much about FRBs, the thing you have heard is CHIME. and the CHIME detections of fast radio bursts over the past 5 years. And so this started in 2019. CHIME is a radio telescope. Here's a picture of it in Canada. It's a cylindrical telescope. It's a transit telescope, so sources transit overhead. This telescope is at a much lower frequency than other telescopes which had detected fast radio bursts. CHIME observes at 400 to 800 megahertz. Other telescopes, all the bursts we've shown so far were detected at a central frequency of 1.4 gigahertz. So it wasn't clear whether CHIME would even actually be able to detect FRBs at first, because interstellar and intergalactic scattering could be too much. It could have been too much to even detect them at these low frequencies. So it was a real relief that CHIME could see them. Here are the 13 bursts that were published in the initial paper. This plot shows the scattering time to these bursts versus the dispersion measure. The black dots are pulsars. The blue points here are non-CHIME FRBs. And the red points are the CHIME FRBs, the circles are measurements, these triangles are upper limits. This is really interesting and important for a couple reasons. The first reason is, and it looks like the scattering towards these fast radio bursts is lower than for pulsars. And this is consistent with most of the dispersion measure being due to the intergalactic medium and not to the Milky Way or a host galaxy. And that's really important because it shows that we can use these fast radio bursts to probe the intergalactic medium. The other important point, of course, is that because they are lower, there's going to be a whole lot more of them detected at these low frequencies. This lower than usual scattering means that it won't be prohibitive to use CHIME to detect more of these. So this was very exciting. In 2021, the first CHIME catalog came out with an astounding 536 fast radio bursts. I think I almost cried when I saw this paper because I thought back to that first Lorimer burst that we had found and how many years we had to wait to see even one more detected, and to see 536 of them in this catalog was just astounding, really. I'd like to tell you that once this catalog was published, the picture became completely clear. There are no more questions about FRBs. We know exactly what makes them, where they're from. But unfortunately, it seems like the more fast radio bursts that we find, there are more questions than answers. Kind of the more we know, the less we know. So of these bursts found by CHIME, about 10% of them appear to be repeaters. So 10% of them we see multiple bursts from the same position and dispersion measure. CHIME cannot localize FRBs. It doesn't have a very good, just like other single dish telescopes. It can't localize them to a galaxy. So not very many of these CHIME bursts are localized to galaxies, but of the ones that are, the picture's pretty confusing. So for instance, one of them is in a nearby spiral galaxy, so a galaxy quite like the Milky Way, not too far away. One repeater is in a globular cluster. This is really weird. Globular clusters are old, right? We don't expect young neutron stars, which was sort of the predominant hypothesis to exist in globular clusters. How did this thing get formed? So there's a lot of mysteries came about from these CHIME discoveries. Okay, and it's becoming clear as more and more of these fast radio bursts are detected that there may be multiple classes of FRBs. Some of this goes back to the host galaxies and the different kinds of host galaxies and environments they're in. But some of this comes from the properties of the fast radio bursts themselves. So if we look at repeating FRBs here in orange and one-off non-repeating events here in green, it looks like the one-off FRBs generally have larger bandwidths. They're detected over the whole radio band, and they're generally narrower. Whereas the repeater bursts generally have narrower bandwidths, and they're generally wider. And so these are kind of like the four different morphologies that we see for these fast radio burst pulses. The one-offs kind of look like this. They're usually pretty boring, Gaussian, detected over the whole band. The repeat bursts are way more interesting. They're often narrow band, they often have multi-components. They show this kind of weird drifting structure. It's kind of akin to what you might see in solar bursts. So it seems pretty clear that there's maybe a couple different mechanisms for FRB production at play. Okay, so a little bit more of the story. The story got pretty exciting in 2020. So in 2020, a very, very bright pulse was detected from a magnetar, a neutron star with a very high magnetic field, detectable as a soft gamma repeater in the X-rays, 1935 plus 2154. This has been known about as a high energy source for many years. And in 2020, a very, very bright radio burst, and in fact, two closely separated bursts, were detected simultaneously by the CHIME collaboration and also by a small telescope called STARE-2 in California. And this plot here shows this, brightness or spectral luminosity. Duncan showed one of these versus duration of all the transient radio sources that we knew, the short duration ones. And you can see here are the pulsars, here are these sporadic neutron stars, which we call RATs, here are the Crab giant pulses, here are FRBs, and this here is this STARE-2 source, this burst from this soft gamma repeater. So it's not quite as bright as the fast radio burst known at the time, but it was a heck of a lot brighter than anything we had ever detected in our galaxy, including a huge number of Crab giant pulses. So this appears to be, kind of a galactic FRB, not quite bright enough, but it shows that it's quite plausible that at least some of these fast radio burst pulses could also be from magnetars, these very high magnetic field neutron stars. This was an important moment for understanding what FRBs are. So in these last few slides, just a little bit about the kind of current status and the future of fast radio burst science. So currently, if you go to the FRB catalog online, you will find there are 789 published FRBs. There's a whole lot more of them that have been detected by the CHIME telescope that are awaiting publication. 56 of them are repeaters, so something like 10% of them appear to repeat. Of course, that number is going to go up with time as more of these non-repeating ones are observed for longer and may end up being repeaters, although it seems pretty clear that not all of them will repeat. Some of them have been observed for very long amounts of time without any repetition. 45 of them are localized to host galaxies, and these galaxies are pretty diverse. Most of them are star-forming, but not all. And if you look at the positions of these fast radio bursts with respect to the galaxies, some of them are right in the spiral arms, where you might expect young neutron stars to be. Many of them, though, are not. They're a little bit off the spiral arms or near kind of like fainter or not very prominent spiral arms or outside of spiral arms and the galaxies altogether. So there's a huge richness and diversity of locations in galaxies where these fast radio bursts are formed, and it's a very complicated picture, and I think we will be at work for many more years trying to exactly figure out the origins of these fast radio bursts. One important clue that was found a few years ago is that a couple of fast radio bursts show periodic or seasonal behavior. So 2 fast radio bursts appear to have active times. And the periodicities are, weeks to month to half a year for 121102. So they appear to emit a lot of bursts in some time frames, kind of shut off in other time frames. This was very unexpected when it was found because we had been looking for periodicities for quite a long time. Other telescopes also, in addition to these periodicities, another important thing is other telescopes have gotten into the fray of FRB searching. This is a picture of the FAST telescope in China, which is extremely sensitive. And that telescope, for instance, published a paper with 1,652 bursts from that original repeater. So this field has just really exploded. So of course, these kinds of periodicities are reminiscent of some kind of binary system hypothesis for fast radio burst origins. Of course, they're not detected for most FRBs, but possibly, we might be looking at a neutron star in orbit with another star, perhaps an OB star with a strong stellar wind that obscures the burst at some parts in the orbit and allows that there's a frequency dependence to the detection of these bursts that needs to be explained by some kind of model. So maybe there's some kind of shock interaction or a binary scenario that can explain those on-off periods. Okay. In 2023, the most distant FRB so far was detected. This thing is coming from 8 billion light years away, so truly cosmological. And just to put the energies of these things in perspective, the energy of this burst that traveled 8 billion light years to reach us is as much as the sun emits in 16 years. So this thing is incredibly energetic. Here's an image of the burst. These are some optical images of the galaxy. It's sort of a complicated, morphologically complicated galaxy with a few different components. This shows the localization of the burst on this image. So this is the kind of stuff you're going to be seeing a lot more of over the next few years. In 2024, the DSA-110, this is a telescope with 110 small dishes in California. They published their first FRB catalog, and here are the bursts that they published. Here are the optical images of the host galaxies. This is just incredibly beautiful and exciting work. And the important thing about this DSA-110 is that unlike many of these other galaxy localizations, they've come from a single dish detection of a fast radio burst, and then a follow-up with an interferometer, which means you can really only do it for the repeating ones, right, where you're going to get another burst. DSA-110 detects and localizes all at the same time. ASCAP in Australia also does this. So you have a more unbiased sample of the kind of galaxies that all of these bursts are coming from. You can see just from this one image, the diversity, right, of shapes, the diversity of spectral behaviors that you see for these bursts. Some of them have fine scale structure, very narrow structure, and this one here. So these are so much science. It's really exciting just to see these plots and these images of these galaxies. A couple things that I just want to point out. I know we're almost out of time. One very important relationship that applies to fast radio bursts is the Marquardt relation. So this is named after J.P. Marquardt, who first posited this relationship. And so it's between the extragalactic contribution to the dispersion measure for fast radio bursts versus their redshift. And what you can see when you look at this plot is all of these dots are the localized fast radio bursts, the ones with host galaxy associations and hence measured redshifts, versus their extragalactic DMs. And you can see this line here is the prediction for that extragalactic DM. And what this means is the DM with the Milky Way contribution, or the estimated Milky Way contribution subtracted. This is the prediction, this colored line here, for a model of the intergalactic medium. And these are the measurements. The red ones are these DSA-110 bursts. The white ones are the other ones. And you can see, that they all lie above this prediction just due to the intergalactic medium, which means there's some host galaxy contribution, as expected, right, to these dispersion measures. But you can also see that they roughly follow this line. And this is really, really important because it shows that if we get enough of these things and we can average out those host galaxy contributions, we can improve our models of the intergalactic electron density, right? Or conversely, just from the dispersion measures alone, figure out roughly how far away these things are. So this is a really important relationship. Another thing that was done in this Law and All paper is look at the delay time distribution for fast radio bursts. So this is the delay between the start of star formation in a galaxy and a source, right? And so you can look at this for supernovae, gamma ray bursts, all sorts of source classes. And this compares the FRB delay time distribution, which still has quite large error bars, here it is, with those of other source classes. And the interesting thing here is that it's very broad. So some FRBs appear to have happened, very soon after the onset of star formation, which would indicate they come from, massive stars, right? Like young stellar populations, like young neutron stars. But some have happened well after the onset of star formation, which might indicate they come from older stellar populations. So again, there's lots of evidence that points to maybe a two origin story scenario for fast radio bursts. Okay, finally, one thing which is, probably a few more years down the line, but if we can find enough of these fast radio bursts, average over the host galaxy contributions, we can both measure redshift and then from the dispersion measures have an independent estimate of the distance, which gives us yet another way to measure the Hubble constant. And so this is a 2022 paper with an estimate, a Hubble constant estimate from this, and the error bars are quite large, but with time, this is going to get better and better and better. So these FRBs are going to be a very powerful tool for cosmology, for understanding the intergalactic medium, for understanding the expansions of the universe. And the future looks very, very bright. So there are several arrays being planned right now, which are going to be extremely sensitive to fast radio bursts. One of these is the DSA 2000. So this is an array of 2,000 small dishes, which will be built in a valley in Nevada. Here's a picture of it right here. The collecting area will be similar to Arecibo, but it's going to see the whole sky and be able to localize fast radio bursts immediately. It's expected to detect about 10,000 FRBs a year. The Chime telescope that we discussed earlier is also being upgraded with outriggers. So there's a few outriggers which are stationed in the United States and Canada. I was just at Green Bank last week and saw the Green Bank outrigger. It's completed, it's being commissioned, it's taking data. And so when these outriggers work together with Chime, they will be able to localize fast radio bursts to arc-second precision, which is also going to be a huge game changer for understanding their origins. They should localize about one a day or something like this. So not all of the Chime bursts will be bright enough to localize with the outriggers, but something like one a day or hundreds of FRBs a year. Another telescope called CHORD, which is sort of like the next generation Chime, should have a similar FRB detection rate to DSA 2000. And of course, all of this radio transient science is very synergistic with all of the optical surveys, right, for transients that are currently going on, and these deep optical surveys that will identify host galaxies for fast radio bursts without need for all the dedicated optical follow-up observations that have been necessary so far. So it should be an extremely exciting next decade for fast radio burst science. It's been amazing to be part of this story. I think that when we first found this first fast radio burst, we knew we were onto something new, but I don't think any of us could really have imagined how this story would unfold and the richness of this completely new field that has been developed in a relatively short span of time. So I'm going to leave you, unfortunately, with just a lot of open questions. And so I'm not going to go through all of these in detail, but there's lots of things that we're still not quite sure about. How many FRBs repeat? Exactly, what are the event rates for these FRBs? Surveys have different selection criteria. There's lots of different selection effects. It's hard to, pin down an exact event rate. Are there different event rates for different subclasses? What about these timescales? I mean, every time we look with different time resolution, we find narrower features. Perhaps there's more very long timescale quasi-periodicities that we'll find once we have much longer observation spans. Are we ever going to understand the emission mechanism? There are a lot of papers out there, but there may be. I think we're now at the point where there are fewer papers than FRBs, but still there are almost as many emission mechanism papers as there are discovered FRBs. So, yeah, and of course, the big endpoint is how can we use these as probes of the universe in ways that we haven't been able to use radio sources thus far. They're really a very powerful new probe. So I think I am going to go to our final slide. And I'll invite Matthew and Duncan up, and hopefully we have time for questions. And we just want to end by thanking, first, the Shaw Foundation for this prize. It was really a shock and an honor to receive this prize. There's a picture of us at this ceremony in Hong Kong, which was just amazing. It was an amazing week. We want to thank all of our funders, in particular the National Science Foundation and the Australian Research Council. And our collaborators, I mean, both our collaborators on this paper, but also all of our pulsar and fast radio burst collaborators around the world who make this field just an absolute joy to work in. And so we're just so grateful for all of them.
You might have to use this.
This doesn't work. So now we are open for questions. Yeah, microphone.
I'm just wondering, for that microwave story, which false alarm of the FRB, why does it have a dispersion? Because there's no plasma to produce that dispersion. I didn't understand. I mean, why people suspect that is a FRB?
Why does a microwave?
Why there's a dispersion of that?
It must be something about the magnetometer and the resonance that is happening in the cavity as you open the door. But I don't know whether that's the high frequency waves come out faster when the door is narrow or not. But I know that Vikram Ravi said that there's also a microwave at the DSA site which gives off phenomenally good FRBs.
Yeah. Sorry, I have a question. From your point of view, what are the most popular or most reasonable channels for the formation of FRBs? I mean, maybe it's too early to answer that, but what are your expectations for that?
The most promising channels?
Yeah, I mean, I think magnetars are sort of the one kind of sure thing, because we've seen this galactic magnetar emit a burst that's very similar to fast radio bursts. They almost certainly need to come from neutron stars in some capacity, because you need something very, very compact because they're so short, and you need a large source of energy. So, you know, I think neutron stars have to be involved in some way. And so I think the dominant explanation right now is magnetars, but there do appear to be FRBs with very different properties in different source classes. So maybe some are magnetars and some are a neutron star in some other scenario, right? And we're not real sure.
Thank you very much.
Yeah.
There were numbers given for the energy per pulse. I presume that is assuming isotropic emission. Is that correct?
Yeah, you have to multiply that by the beaming fraction, which could be quite small. But it does appear that there is no regular periodicity on sort of timescales of milliseconds or seconds. So we don't believe that FRBs are like beamed in the same way as pulsar is beamed. So that they could be more isotropic than a normal pulse.
So you already answered half my question with what do you think is the progenitor mechanism? So I'm going to ask a different version of it, which is, you replied based on data, but I'm wondering how you felt when you first saw that burst, if you had a gut instinct for what is the physics that I'm seeing here.
We can all have a go.
Yeah. Go ahead.
Yeah, so the thing that struck me was just how much it looked like a pulse from a pulsar. So I've been looking at pulsars at that point for 20 years in my career, and it just looked remarkably like a dispersion sweep. And often when we commission an instrument, we'd look at the filter bank data on a bright pulsar just to see what it looks like. So it was instantly recognizable. I think I had trouble getting my head around the fact that it might be 10 to the 12 times brighter than a pulse. And I think that required a bit of an act of faith, which took me many years to have.
Jump in? Yeah. Yeah, I mean, when I first saw it, it looked like a pulsar pulse, but then once we looked at the energetics, the very first thing that came to my mind was the coalescence of two neutron stars, just because if you work out the energetics, it was just about right. You could get just about that much energy. I had been working in gravitational waves, and so I think about that stuff a lot, and so that kind of, I don't know, that was one of the first things that came to my mind without any theoretical background on exactly, whether the spectrum would be right or the width would be right. But the energetics kind of worked out, and because we only saw this one, it seemed, I at first thought it had to be something that was cataclysmic, right? Some kind of thing that we were never going to see again. So a neutron star merger was kind of the first thing that came to my mind, and I imagined all this exciting sort of LIGO, FRB coincidences, which haven't actually panned out really. But that was my first thought.
Yeah, I think definitely those were going through my mind. Just on a slightly different topic, one thing that, going back to 2007 that was going through my mind as well was that already at that point I'd spent quite a bit of my career doing low number statistic studies of pulsars, for instance, double neutron star binaries. Back then there were only a few known, and we would make wild extrapolations of event rates based on only a few systems. But we were fairly confident in what we were doing in that particular case, and that's turned out to be more or less okay. And with this one, I think, as Matthew mentioned, that dispersion measure sweep was the real thing that kept us going, when we would have doubts going forward. But it was, an amazing thing to just be a part of.
Thanks. That galactic FRB, in one of your plots, the STARE-2 event, in one of your plots you had it at, I think, a lower luminosity than the bulk of the FRB, the cosmological population. Is that potentially due to selection effects, just where our telescopes aren't sensitive enough to detect cosmological FRBs that are that faint, or?
Yeah, I mean, I think, we couldn't detect them far away if they were that faint. So I think, I think it could be all FRBs, if they repeat, could have a luminosity distribution that extends to the same luminosities as that FRB from that soft gamma repeater, but we just wouldn't see them if they were in these other galaxies. Yeah, that's a good point. Yeah.
Okay, so I don't see any more hands, so we'll close this session, and let's thank the speakers one more time. Thank you so much.
Test. Good afternoon, everybody. Can we please take our seats? Please be seated. Can I also ask everybody sitting on the outer edges to try and move as center as possible, please? There's a reason for it that you'll understand later. So everybody sitting on the outer edges, if you can move a little bit closer to the center. If there are seats in the center row, if you can occupy those. And those sitting on the far edges, on the very edges, those sitting looking at me, wondering what I'm saying, I'm asking you to move towards the center, please. Thank you. Same on that side. If you can move towards the center. It's going to have to happen later on anyway, so I'm letting you do it now for a very specific reason. Those coming in through the top, if you can take your seats very quickly, please, so we can start the official program. Thank you. The sooner I have everybody in their seats, the sooner we can begin. Want an introduction there? Yes. Okay. Yeah, absolutely. About that in detail now again, because I had a different visual there, but we'll talk about that. Okay, you guys will talk about that. One more time, please. We are wanting to start the official program. I need everybody at the top seated. And it's very important that those who are sitting on the outer edges move closer to the center. So if you're sitting on the outer edges over there, I need you closer to the center, please. Even if it is in your own row, that's fine, but closer to the center. The gentleman at the top over there, I need you closer to the center, please. 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 Rinse and repeat, please. Over here, same thing. Can I have you closer to the center, please? Can somebody please record me saying that and just put it on repeat? Thank you. With subtitles. That was a lot more effort than I thought it was going to be. Give me a second and you'll understand why all of this is happening. Standing in front of a door that's going to open. Ladies and gentlemen, again, good evening and welcome. May I please ask you to stand for South Africa's Minister of Science, Technology and Innovation, Dr. Blade Nzimande. Thank you. I don't know how any MC follows up on that. That's the Itemba Choir with your opening medley. Good evening, everybody. Welcome to Cape Town. How are you doing? Is everybody well? Did you enjoy that? Yes? I tell you what, you didn't see that in South Korea 3 years ago, did you? I'll tell you another little something. You're not going to see that in Rome 3 years from now either, because that is distinctly African. And we took a long, long time to think up how we are going to make you feel welcome to the very first General Assembly of the IAU in Africa. It's long overdue, don't you think? "96 years of General Assemblies by the International Astronomical Union, and not once in Africa, and that can never ever be said again." It's going to be jam-packed full of all sorts of wonderful things that are distinctly African, distinctly South African, and particularly Cape Townian. Quick show of hands. Who of you is the first visitor to Cape Town as of now? Quick show of hands. Wow. So that's about 80% of this crowd is in Cape Town for the very first time. Would you like me to teach you how to say a hello in Cape Townian or how to swear in Cape Townian? Which one's better? A little bit of both. No, I won't. So there are 11 official languages in South Africa. There's one hello that applies to all of them. Would you like to know what it is? It's distinctly Cape Townian. It's a word that was born in Cape Town, and it has been exported all over this beautiful country of ours. The word is very simply aware. Aware, if you want to add Maymasakant, you're welcome, but aware will do. And if you forget it, just think of awareness. Aware, it's a slight variation, but if you say aware to a South African, you're either going to get smacked in the face or they're going to say aware back. Good luck. No, I'm kidding. I won't get you into trouble. I want you to come back. I want you to enjoy this beautiful city of ours. We've got it ready for you for the next 2 weeks, and it's going to be absolutely phenomenal. This gathering, this General Assembly, the 32nd one by the IAU, has been funded and sponsored and supported by a whole host of people. I'm going to introduce you to a whole lot of them over the course of the next hour or so before we introduce you to another distinctly Cape Townian bit of entertainment. You are going to absolutely love it, but that's a little while from now. Firstly, your host for this evening, the main host, is South Africa's National Research Foundation, and I would like to invite the CEO onto the stage to come and address us as our first official matter of the evening. A warm round of applause, please, for Fulafelo Nelwamondo.
Director, Minister of Science, Technology and Innovation, Professor Blade Nzimande, and the entire DSTI leadership that's available here. Madam President for the IAU, Professor Deborah Elmegrin, and the entire IAU leadership, CEOs, and the heads of entities that are represented here, university vice chancellors, and the members of management teams of various universities, local and abroad, who are here. I've seen quite a few. Members of the diplomatic corps, ladies and gentlemen, distinguished guests, away. What I got back was the laughter. Let me welcome you back to Africa, where people greet back when they're greeted. So away. That's it. I won't go through a full list of dignitaries that are here. I've actually taken a risk of delegating upwards to my minister. So if I lose my job, we understand why, because I've delegated upwards, but he will take us through that when he gives a talk later on. So I've been given a very quick task. One is just to welcome you, but the choir has done a fantastic job in welcoming you already. So those who don't understand, I will try to interpret what they were saying in my remarks. But the second component of my conversation is just to introduce the keynote speaker, who will then come on later on. Firstly, on behalf of the National Research Foundation and the Department of Science, Technology and Innovation, and the African Astronomical Society, it is my great honor and pleasure to welcome you to South Africa. I'm actually impressed by the number of hands of people who are in Cape Town for the first time, so let me also welcome you on our continent. I would also like to formally welcome you to the 32nd IAU General Assembly, a gathering of some of the brightest minds in astronomy and related fields. We are really honored to have all of you here for the next 2 weeks, this week and next week, as we explore the latest advancement and future directions in the field. Like many developing countries, South Africa faces a number of challenges. Prominent among these challenges are inequality, poverty, unemployment, and the challenges around the sustainable use of our natural resources. Despite the many challenges that South Africa has faced, we have continuously invested in astronomy with appreciation of the number of technologies that can come out of astronomy. If you look at it historically, you can see a number of technologies from the CCDs to the internet and the Wi-Fi, to how astronomy has changed the gains in photography, to the telescopes and instruments building, to signal processing, to medical imaging, and many more. As Africans, we always look at the stars for guidance, and most importantly, for the wisdom regarding the seasons, knowing when to plant, when to harvest, and so forth. So in making these investments, we have pinned our hope on that the return of these investments will soon be visible to everyone. They need to fully understand the origin of the universe, life, and humanity holistically have always been at the core of what we wanted to understand so that we can know how we can actually move our society forward. We have always recognized the role that astronomy can play in developing our continent, factoring the geographic advantage that we have in many parts of Africa and in the Karoo here in South Africa. Esteemed colleagues, this year, 2024, South Africa celebrates 30 years of democracy. We would not have wished or asked for a better celebration than adding to our celebrations hosting this General Assembly, which is taking place for the very first time on the African soil. Please give IAU a round of applause for that. Secondly, this is happening now in August. In August, South Africa will celebrate Women's Month, remembering the struggles and the sacrifices that many women have put for the survival of this country, starting in 1956, on the 9th of August. So to all the women who are here, I want to congratulate you, and I want everyone to give you a warm round of applause. Distinguished guests, I've mentioned that my task today is very easy, was just to welcome you, and the choir did the job for me. The second part is for me to introduce the keynote speaker, who will speak a little bit later. But I was asked to just introduce them now because they won't be introduced by a person. They will get an African introduction later on. So let me just do a very quick introduction to our keynote speaker. Tonight we have a distinguished guest who has made significant contributions to the realms of science, technology, innovation, and higher education in South Africa. It is my privilege to introduce our esteemed speaker, our Minister of Science, Technology, and Innovation, Professor Bonkosi Emmanuel Blade Nzimande. I often don't say all his names at once, but today I've done it. His career is marked by a profound commitment to advancing education and fostering innovation. Under his leadership, there have been numerous initiatives aimed at strengthening our scientific community and enhancing research and development across South Africa. With qualifications in psychology and industrial psychology, and later doing his PhD in sociology, I have no doubt that should there have been a gathering like this in the 1970s, he would have changed his career. And I'm sure he will have done his studies in the sociology of astronomy or something of that nature. I'm sure Professor Nzimande will have focused on the intersection of astronomy and social sciences in addressing problems such as mental health, something that he's very passionate about. His dedication to integrating science and education policies, as well as integrating social sciences and humanities with the STEM sciences, has paved the way for many opportunities and advancement that benefit our society as a whole. So please join me in extending a warm welcome to Minister Nzimande, who will give a talk a little later and he won't be introduced again. Minister.
Thank you very much, Fellow. The Minister will, of course, join us a little bit later for the official keynote address, but that is the CEO of the National Research Foundation in South Africa, Fellow Nell Wamonde. So the next person, I had a chat with her a little bit earlier. In fact, I think she arrived yesterday. And in case you'd like to know, you must be wondering, who's this man who keeps on talking to us and why doesn't he introduce himself? How rude. The reason for that is because I wanted to tell you the story. My name is Bobby Brown, and I'm a broadcaster here in South Africa. And my field of interest in broadcasting is science and science communication and tech communication. So I'm always looking for, I'm a bit of a groupie when it comes to scientists, a bit of a science geek. I love them to bits. So whenever I run into somebody who looks like they're smarter than I am, and that's pretty much all of you, then I grab my mic and I want to interview them for my radio show. And this is what I did with this lady yesterday. And the first question I asked her, I said to her, on a scale from 1 to 10, how annoyed do you get when people confuse astronomy with astrology? And she said it's a 9 every time. And then my next question to her was, so what star sign are you? And she practically attacked me right there in the interview room. So I won't do that again to her. Folks, can I ask for a warm round of applause, please, for the president of the IAU, Deborah Elmerine.
Away. Thank you, Bobby. Welcome, Minister, welcome, honored guests, and all of our participants, whether in person or online, to Cape Town for the 32nd General Assembly, the first ever on the African continent. It is wonderful to finally be here. The preparations, led by Kevin Govander, Vanessa McBride, and Charles Takalana, and their terrific National Organizing Committee, have been underway since the winning bid was announced at the 30th General Assembly in Vienna in 2018. I'm very grateful for all their efforts and to the NRF and DSI for their commitment to this General Assembly. As the world comes to Cape Town, in person or virtually, we celebrate the rich history of astronomy in Africa as we present our research, initiate new collaborations, enjoy networking, share astronomy with the public, and explore the local beauty. And boy, is it beautiful here. August is designated as Africa Astronomy Month, an appropriate cap to the Vision 2024 efforts that have united Africans in their preparations to share their astronomy with the world. Astronomy is rooted in all cultures and invites broad thoughts about our place in the universe and on our fragile Earth. Astronomy in Africa began at least 7,000 years ago with a stone circle known as Nabta Playa in Egypt that predates Stonehenge by about 2,000 years. International observational survey work was led by astronomers at Cape Town over 2 centuries ago and continues with the present-day SALT at the South African Astronomical Observatory. The Meerkat radio array is a precursor to SKA, the KELT and SuperWASP telescopes, the Hess Gamma Ray telescopes in Namibia, among many others in Africa. South Africa became an IAU member in 1922, shortly after the IAU's founding. Other African national members include Algeria, the Republic of Botswana, Egypt, Ethiopia, Morocco, Madagascar, Mozambique, and Nigeria. Africa plays a vital role in IAU activities. The Office of Astronomy for Development, headquartered here in Cape Town, has engaged thousands of people in projects that draw on the excitement of astronomy and apply its technologies through local key programs to achieve UN Sustainable Development Goals. African countries have hosted several IAU symposia, workshops, and international schools for young astronomers over the years. African astronomers have held many IAU leadership roles, including Vice President Solomon Tessema from Ethiopia, and past Vice President Rene Kron-Kortreg from South Africa, and several others on steering committees of our scientific divisions, commissions, and working groups. We welcome 536 new individual members and junior members to the IAU this year, approved at our recent executive committee meeting. We will also be announcing new honorary members and new national members at this General Assembly. We have an exciting schedule planned with lectures from international prize laureates, plus talks and posters, including many by early career astronomers. The plenary talks invited discourses, symposia, focus meetings, meetings of the offices and the Center for the Protection of the Sky, executive committee working groups, division days, women in astronomy and young astronomers lunches, business meetings, and outreach and social events encompass all aspects of IAU activities. These events further the goals as laid out in our 2020-2030 strategic plan presented at the General Assembly back in Vienna, and for which we just completed our midterm review, which I sent to IAU members in June. These goals include coordinating research efforts and communicating astronomical knowledge among professional astronomers, promoting the inclusive advancement of astronomy, promoting the use of astronomy as a tool for development, engaging the public in astronomy, and stimulating the use of astronomy for teaching and education. The important point is that astronomy is for everyone. With the full engagement of Africa in astronomy, including the admirable efforts to make this meeting open access, this is truly an historic General Assembly. I wish you all a memorable meeting. Thank you.
That's right. She's one of the smartest people in the room because she's a quick study. She learned that greeting very, very quickly there. The aware greeting. Are you guys quite familiar with the aware now? Would you like to learn some more South African languages? Yeah? I'll tell you what we're going to do. A little bit later, we'll bring the choir back onto the stage. I just had a word with them. And I've asked them to prepare the South African anthem for you now. I said to you that we want to give you an authentic African experience. There are very few national anthems in the world that are quite like ours. Ours is quite unique, and I'll tell you why. It incorporates 4 of our official languages in one song. Now, I think you'll get the English bit quite fairly easily. If there's anybody in the audience who's German or Dutch maybe, and what's the other one? Flemish. If you speak Dutch, Flemish, German, maybe a bit of French, you'll get the Afrikaans bit of the national anthem. And then, just because we want to confuse all the foreigners, we threw in a little bit of isiXhosa Now, there's no language in the world that compares with isiXhosa. So I can't say, hey, if you understand a little bit of Japanese, you'll get it. You won't. We've thrown in a bit of isiZulu and some isiSotho for you guys. We're going to throw the words of the anthem up on the big screen. Your job is to sing along to every single word. We're going to be watching, and if you don't, that's the end of the General Assembly for you. We've got cameras. If you're just miming, you're going to get into trouble, especially when we get to the Zulu bits. We're going to be watching you. All right. Folks, this is a big gathering. There are a lot of you. Some of you are here remotely. Some of you are here in person, obviously. This takes a mammoth undertaking, a military operation, and of course it takes lots and lots of monies. So there are a couple of funders who helped us put all of this together. One of them is the Simons Foundation. They've apologized. They are unable to be physically present here today, but we're used to all this online stuff and video stuff. So we did ask a representative, David Spiegel, from the Simons Foundation to join us on video this evening.
Greetings. Oh, hello. I'm David Spiegel. I'm president of the Simons Foundation, and I want to welcome you to this year's General Assembly meeting. I regret that I won't be able to join you in person, but want to express our welcome on behalf of the Simons Foundation and our pleasure in being able to help support attendance at the General Assembly. The Simons Foundation was founded by Jim and Marilyn Simons 30 years ago. And while Jim Simons passed regrettably this year after a long and impactful life, the mission of the Simons Foundation remains the same: to support basic research in mathematics and science. Our goal is to enable transformational work in math and science. And one way we do that is by enabling conversations that wouldn't happen otherwise, because it's those conversations that often lead to novel insights and novel ways of doing things. And one of the most valuable ways of promoting these conversations is bringing people together at meetings like the General Assembly. And this is why we're so pleased to be able to provide support to enable more astronomers to attend the meeting, particularly those from throughout Africa. Africa is poised to play an increasingly important role in the scientific community writ large, but particularly in the astronomy community. And we're happy to be part of this meeting. For those of you who are attending your first IAU meeting, I want to welcome you. I remember my first meeting, and I want to encourage you to take advantage of it. Meet new people. Go up to people you don't know. Ask them about their work. Go to sessions that you won't normally go to. Learn about the breadth of what's going on in astronomy. This is a chance to really broaden your horizon, make new connections, and that will enable you to do even more impactful work in the years to come. So welcome, and we're so pleased to be part of the IAU General Assembly.
One of the kind sponsors of our gathering here, the Spiegel Foundation, the others, as I said earlier, the National Research Foundation, and our departments of science and innovation, whose minister is present here this evening. You'll hear from him in just a little bit, but the reason why you even know anything at all about South Africa, the reason why you can maybe mention one or two or three, now 4 with me, South Africans, is because of a very particular body whose job it is to publicize South Africa to the world. And they've had a big hand in our gathering here this evening. So if I can invite onto the stage, from Brand SA, Lerato Legobe.
Honorable Minister, Madam President of the IAU, distinguished guests, Dumelang, Absheni, Molweni, Realocha, and good evening to you. Away, away, Masakent. As Brand South Africa, the entity tasked with packaging and telling the good story of South Africa and its offerings and capabilities on the global stage to position South Africa competitively for investment promotion. We are proud to be the host nation for this historic engagement. It is therefore my esteemed privilege to welcome you to the home of vibrant, diverse cultures, as you saw, immense humility, resilience, and passion, often expressed through song and dance. South Africa is renowned for its natural beauty, its sporting prowess, rich cultural heritage, our championing of human rights, and for being the friendliest nation in the world. Yet beyond these attributes lies Africa's most advanced and diversified economy, standing as a beacon of opportunity and resilience. Our economic diversity forms the foundation upon which we are building a future of sustainable development and inclusive prosperity, underpinned by innovation, research, and development. Technology, innovation, scientific research, and most importantly, collaboration will propel us to new frontiers of socio-economic possibilities. We must harness our collective strengths to build prosperous sustainability and inclusive future for Africa and the world. The 2024 IAU General Assembly offers a unique opportunity to showcase South Africa and Africa's growing contributions to astronomy, promote regional and international scientific collaboration, and inspire the next generation of scientists in the region. Distinguished guests, it took us 100 years to get to the motherland, to get to our beautiful country. We hope this will mark the beginning of many such engagements that will showcase our contribution, our global contribution in this field. We also hope that you will take the time to go see the beautiful sites we've got in Cape Town, to go eat our beautiful, authentic South African food, and have a unique, beautiful South African experience, so that you can be the foot soldiers to tell about our beautiful country. Thank you very much for joining us, and we do hope that you will make the best of this experience. Ralebo.
This is who we are. More than 60 million different voices echoing in harmony from the southernmost part of the continent, where ordinary people have carved their names in an extraordinary history by showing the world that peace is always better than war. Our reach is not limited by our borders, bringing joy in people's hearts and a spark of rhythm to their moves. This is the welcome home of opportunity, inspiring millions to look here in search of a better life, and sharing our best with the world. We are home to undulating mountains, flowers, endless seas, the beautiful animal kingdom, and the ever-changing seasons that color our world. We are the birthplace of humanity and a showcase of human excellence. We believe in South Africa. We are inspired by our victories of the past and our strong institutions to overcome the challenges of today and build a better tomorrow. This is who we are, South African. South Africa, inspiring new ways.
This is a message by Brand South Africa.
We call it the most beautiful country in the world, and we are happy to have you here. Are you ready for your moment? Before we get to your moment, let me just qualify something for you guys very quickly. When very important people join us in South Africa, we're a very unique thing. Up north in Europe, across the Mediterranean, you applaud. Across the Atlantic, you put your hands together and you applaud. We've got a thing in Africa that we do. It's a praise singer. the praise singer comes and they sing the praises, as it says, of the individual, to tell everybody how wonderful this person is and the amazing things that they've done. And we thought we'll introduce you to this concept. I really want you to export this to Europe. I really do. I really want to see a European leader walking onto a stage and hearing a praise singer, because I've only ever heard praise singers in our languages. I haven't heard a praise singer do this in German or in French. I wonder if it would be as sexy as what you're about to experience. So that's coming shortly in the next couple of seconds to invite our keynote speaker, Minister Bladen Zamande, onto the stage. But as we get there, you enjoyed them earlier, and here they are again. This is the Itemba Choir. Did you guys get the national anthem lyrics ready for me? I asked somebody to go and Google it. Have we got it? We got it. All right. Are the cameras ready? How many? 24, okay. All over, okay. 24 cameras trained on your faces to make sure that you... This is a hallowed moment, as you know. When a national anthem plays, you're required to be respectful, and you are absolutely required to sing along. Folks, the Itemba Choir.
Okay, squeeze in and you can start. Go, go, go.
Ay, magkwetseni! Uthanda thola sanade jonga. Kaloku phuma ubuqaba kaloku kum. Ndingogonqa kumeqolo ndiyaqoqodisa ndiqhubela ngayo ndiqhubela phambili. Kusuba ndiqoba iqhinga xa sendiqalile. Kwizibongo. ndinyathela caca ndisiyamanye ukunyeza ukuba ndisasinandile xa ndithandile ndishimtsha licatekile ukuba ndiyafana nabulele le yiAfrika yinzala yazolo nomhlaba liyeza lokuphilisana kaloku igazi linye kuba nesandla sihlabe sinye singafani nazilwanyana solokuze siphile ngesinye le yiAfrika kuya kuthi kokuphuma ilanga kuthetha ubumnyama kuvela ukukhanya isizwe sifumbathe ukufudumala sisinde kuloo madala kufe qabaka nengqele ngomzimba ngenantaka silibuka ngokuchulumanco litye losithela ngapha kwentaba le yiAfrika kuya kuthi kawunemvula kungqongqa izulu kuvokohle kumhlaba libe lizela intsikelelo neziqhama ndithethi ke ngentyatyambo ngevumba umphefumlo nencinga sifumane ukuphumla kumdudu ngamapasa kuba yona lehlabathi ngumtyanathunga. This is Africa, our nation. Ndingogonqa kwemiqolo ndiyaqoqodisa ndiqabela ngayo ndiqhubela phambili. Yegam. Yoho.
Can I be honest with you for a moment? Just a brief moment, if you'll allow me, with advance apologies. There are few things as utterly pleasant as seeing an entire hall of confused European faces. Because in truth, you guys always look like you know everything. You know what I mean? You look confident, you see a European face and you go like, well, they look like they know what they're doing. But we designed that moment specifically. Ladies and gentlemen, our Minister of Science, Technology and Innovation, Dr. Blade Nzimande.
Program Director, thank you very much. Let me start by greeting the President of the IAU, Madam Professor Deborah Elmer-Green, and the members of the IAU Executive Committee, President of the African Astronomical Society, Professor Thebe Medupi, NRF Board Chair and Vice Chancellor of the University of Cape Town, Professor Musa Mushabela, and the NRF CEO, Dr. Fulufelo Nolamonde, our host organization, leaders of the South African National System of Innovation and Higher Education, the Director General of the Square Kilometer Array Observatory, Professor Phil Diamond, members of the Diplomatic Corps, members of the media, distinguished guests, ladies and gentlemen. It's indeed my honor and privilege to deliver this address to this prestigious occasion of the International Astronomical Union General Assembly, which is the world's largest body bringing astronomical science across the planet together. This year's assembly is particularly special to us as a country, as it is the first to be hosted on the African continent. And our slogan from the time we first proposed this event to be held here has been, it's time for Africa. In one of our languages, the Sotho languages, we simply say, Kinako. It's time. And it is hoped that the conference will showcase the current contribution of African astronomy to global astronomy and its future development. The hosting of this first ever IAU General Assembly on African soil is a great privilege, not only for our country, but the entire continent. On behalf of our President, Mr. Cyril Ramaphosa, the President of the Republic, and the people of our country, I wish to extend a special South African welcome to all the IAU delegates to South Africa and say you are most welcome. Namugelekile. It is perhaps also fitting at this moment to remind ourselves of the continuities across ancient and modern timescales of African astronomy that predates contact of its indigenous communities with Europeans and which spawned indigenous knowledge in mathematics, physics, and astronomy. Of course, these advances in early African knowledge, as the president of the IAU has indicated, of celestial systems and forces, were closely tied to the survival and evolutionary history of those Africans. For example, the nomadic peoples carefully studied astronomy in order to guide their travel across the desert regions. As part of controlling the Nile Valley and agricultural cycles, the ancient Egyptians studied the skies to predict the world's first 12-month, 365-day calendar. During the 14th century in Timbuktu, in Mali, astronomy was taught as a specialized subject, and scholars came from many parts of the ancient world to study in Timbuktu. The 7,000-year-old stone circle, which the president of the IAU referred to as well, known as Nabta Playa in Egypt, observed the skies, and that has been part of our heritage from time immemorial. Inspired by this history, indigenous astronomy continues to be a major part of our astronomy programs, and it is therefore pleasing that this conference will, amongst others, showcase the cosmic echoes, a shared sky indigenous art exhibition. The story of the evolution of modern astronomy in South Africa is an equally fascinating one. Astronomy was institutionalized in South Africa just over 200 years ago with the establishment of the Royal Observatory on the grounds of what is today known as the South African Astronomical Observatory here in Cape Town, which is responsible for optical and infrared astronomy. Radio astronomy began in South Africa with a 26-meter dish built by NASA and placed in Hartebeespoort in 1961 as a ground deep station used to get data from and sends command to many unmanned US space probes going beyond the Earth orbit. But it was really with the advent of our democracy in 1994 that South African astronomy experienced major leaps on a number of fronts. During the democratic era, two major international telescopes were set up in South Africa, which include the 10-meter Southern African Large Telescope, known as SALT, in Sutherland, the largest optical telescope in the Southern Hemisphere. Then there is the Meerkat Telescope in Carnarvon, which is a precursor to the SKA project. The Meerkat is another amazing achievement on the global science stage, and we wish to thank our international partners, especially Germany, Italy, and China, for their contribution to this project. All these strategic interventions have enabled South Africa to exponentially increase the number of astronomers from 60, and only 5 of them were radio astronomers in 1994, to now about 300 over the last 30 years. This year also, I'm pleased to indicate here, we are launching a new presidential PhD program, which aims to send successive cohorts of students abroad to pursue full-time and split-side PhD studies in reputable, world-class knowledge and innovation institutions targeted at developing critical skills in areas like artificial intelligence, research, advanced biotechnology, fuel cell development, batteries and other storage, and next-generation mining. I am sure that astronomy and space science will benefit from this initiative, given the truly internationalist and multidisciplinary nature of these fields. Ladies and gentlemen, our vision is for South African astronomy to become a global hub for astronomical sciences and facilities, as articulated in our national strategy for multi-wavelength astronomy of 2015. Large-scale investment in the Meerkat Square Kilometre Array endeavor, amongst others, and South Africa's growing international ranking and partnerships in astronomy is characteristics of this growth and expansion of astronomy in our country. The Meerkat SKA project in particular offers us an opportunity to contribute to the knowledge and economy and the big data revolution through international collaborations and the pursuit of world-class research, thereby driving transformation and human capacity development. The SKA is the flagship frontier science partnership of the 21st century, and South Africa remains fully committed to it. I would like to congratulate Professor Diamond on the outstanding progress being made in progressing construction of the SKA here in South Africa and Australia. It is certainly a key commitment of this government's 7th administration to ensure that we empower our continent with high-speed research networks, computational technology, and cloud infrastructures as part of preparing Africa for the challenges and opportunities of the 21st century astronomy. I'm sure COVID-19 has taught us an important lesson. No part of the world will be able to develop sustainably if other parts of the world are left behind. The attempt, for instance, by some countries to hoard vaccines could only contribute to COVID being recirculated even back to those countries if COVID-19 wasn't tackled globally. In fact, that should be our approach to science today. And astronomy is a very important platform through which we can do that. Social legitimacy and sustainability of African astronomy, we recognize how crucial human development is to ensure next generation of technical, engineering, basic and applied scientific skills underpin expansion of our infrastructure. Therefore, as we say, through my department, it ain't science unless it is truly global. I wish to record my special thanks to both Sao and Sarao and their sites in Sutherland and Carnarvon in their remarkable work supporting training of technicians, telescope operators, astronomers, engineers, data scientists, and administration professionals. I'm very pleased also that our Department of Science and Innovation is working closely with the Department of Tourism, led by my colleague, Ms. Patricia Dilil, our Minister of Tourism, in developing the astrotourism sector through community public-private partnerships in remote parts of South Africa. We would like many of you to come back to South Africa as science tourists, which is something very important for our continent. I'm also delighted, as it has been indicated, that this month, in August, we as a country are celebrating women who stood out bravely to fight against apartheid. The fact also that today we have 2 African-American women astronauts, Dr. Sian Proctor and Dr. Mai Jamison, who will be giving public talks and engaging in outreach projects with school learners, is particularly significant for us as South Africa. and especially for women of our country and women globally. There will be also, I'm very pleased, a dedicated program on the 9th of August, which is National Women's Day, as part of this event as we commemorate Women's Day by celebrating the remarkable contributions of women in science and astronomy. It ain't science unless women are centrally involved. I can say this confidently because I call myself a mama's boy, having been brought up in a woman-headed household from age 12. I know that without women in society, in communities globally, our societies won't make progress. The African Astronomical Society has also got a dedicated program for women in astronomy through the African Network of African Women in Astronomy. And this year, the International Astronomical Union of Women in Astronomy will be holding a joint session with their African counterparts at this General Assembly. This session also aims to facilitate discussions amongst astronomers on gender issues and policies supporting the career of women researchers engaged in international mega projects located in Africa, such as the Square Kilometre Array, amongst others. I would also like to recognize the efforts made by the IAU Office for Astronomy Development and the African Astronomical Society, both based in Cape Town, in supporting other African countries to take advantage of opportunities in astronomy. That is why when we say we are hosting this General Assembly as South Africa on behalf of the African continent, we mean it. It's not just an empty slogan. We are working together with the African Astronomical Society, and we've made sure also that we invite other African astronomers to be part of this important gathering. Because as South Africa, we always believe we are not an island in an African continent. We are an integral part of the African continent. The organizing committee of the 2024 General Meeting has also announced that over 3,000 abstracts were submitted, which is an impressive number for such an event and certainly offers an opportunity to share new sources of data and evidence to test through experimental work the explanatory value of the theoretical models developed in recent years. I was doing some interviews earlier today. I must say it has also just increased. I'm a first language Zulu speaker, my Zulu vocabulary to try and explain what astronomy is in isiZulu. So that's one big achievement of this particular conference. The abstracts that we are having here cover a wide array of exciting topics based on the empirical results derived from new missions and surveys of different parts of the cosmos, including remarkable data coming from the Meerkat Radio Telescope and James Webb Space Telescope. In conclusion, I wish to thank the IAU for entrusting South Africa with hosting this prestigious gathering and all the teams which contribute to the organization. This gathering reflects the global astronomy community's commitment to advancing research, fostering collaboration, and addressing contemporary challenges in astronomy and those faced by humanity. Professor Nelo Mondo, you might have said it in passing. Indeed, it is important that astronomy, just like all of natural science, it ain't complete science unless and until it interacts with humanities and social sciences as well. And it is very important because our own philosophy, again, as the Department of Science and Technology and Innovation, we say, it ain't science unless it is multidisciplinary. Because we can't break up societies into biomedical sciences, into astronomical sciences, into psychology, and so on. We are all these things in one. And there is no better discipline to lead by example on this than astronomy. I wish you productive and exciting deliberations and look forward to the outcome of the 2024 International Astronomical Union General Assembly. I thank you very much.
Do you know what I sometimes wonder? I sometimes wonder, like when the Europeans first came here in their ships, right? And then they saw the Zulu warrior, the impi, and they didn't turn around and leave immediately, will always confuse me. I would have seen that and I would go, oh, now let's just move on. This is some scary stuff. And wait till you see actual impis in action. I would have left, but you guys stuck it out. Funny enough, it was stars, wasn't it? It was stars that brought them here, wasn't it? They were navigating by this. This is how important astronomy is. You know, sometimes there's a negative part of astronomy, like the Europeans found us. And there's a positive side of astronomy. Just think about it, right? There was a baby born roughly 2,024 years ago, thereabouts. And if it wasn't for a star, he never would have gotten all those nice gifts. Do you know what I mean? Like gold, frankincense, myrrh. It was a star that he should be grateful for. But that was lovely. It's going to be more entertainment a little bit later. But I want to, those were Zulu dancers. They deserve a round of applause, I think. Again, yes. I'll tell you all what else deserves a round of applause very quickly, briefly, before I introduce the man who pulled all of this together for you. You know, what you guys do in space science is very important. I mean, you shoot a telescope 1,000,000 miles into space, and you park it there, and it looks into the distance, into the past. That's impressive. You blast spaceships into lower Earth orbit, and they circle the Earth, and you put a telescope in there. So fine, the mirrors didn't always work, but then you fixed it, right? That's impressive. But I tell you what's impressive. A radio station that broadcasts everything that happens here today. And there's one here in the main hall. It's called Radio Astro. And I want you to swing by there. It's at stands D17 and 18. That's my team. We're there for the entire 2 weeks. And we might just be interested in interviewing you guys. Come and see what we do. And I'll tell you why it's quite significant. Because what the IAU has done, it's taken a whole lot of young broadcasters from our townships here in Cape Town who want to be science communicators, but they haven't quite got the skill, and they've said, come along to Radio Astro, we will teach you how to do this. And then they got hold of me and they said, do you kind of know what you do? And I said, I kind of know what I do. And they said, you lead this group. So come and check them out. Radio Astro, we're broadcasting live every single day, live stream from 10 o'clock in the morning on radioastro.space. And it's all thanks to, thank you. Minister Bladen Zamande has asked that he excuses himself. He's got another function to attend. Minister, thank you so much. Thank you so much for making the time. Most important part of your outfit, sir, is the hat, because it's cold out there. And when it's cold up here, it's cold everywhere. I know, I know. Thank you, Minister Dr. Bladen Zamande. So the one bit that I don't know a lot about is when the AIU hands out awards. So what we've done is we've asked the Secretary General of the IAU to come up, Piero Bonvenuti. I love saying that, Piero Bonvenuti. And I'm sure I got it wrong, but if you can come and take over for a little bit, sir, and take us through the awards part of the ceremony this evening.
Authorities, dear colleagues and friends, I'm also thrilled to welcome you to the 32nd General Assembly of the International Astronomical Union, the first in the Union long history to take place on the African continent. And I'm fascinated to think that we all have our roots here, the cradle of humanity, from where Homo sapiens, about 60, 70,000 years ago, began his migration that populated the entire globe. I'm even more fascinated imagining that he was guided in his millennium journey by the sun, by the moon, and the stars. He was the first astronomer. And we are returning to his homeland to honor him and the most ancient science, astronomy, with much more scientific knowledge today than our ancestors, certainly, but maybe looking around with not so much wisdom, but certainly with the same curiosity and love about the cosmos. The 32nd General Assembly will be then memorable for many reasons, and we should be proud to be part of it. I'm here as General Secretary ad interim since last November, following the resignation by the General Secretary José Miguel Espinosa for health reasons. And my first thoughts go therefore to José Miguel, to whom we ought to be grateful for his endurance in his position during a difficult time. We wish him all good in his recovery path. We should also express gratitude to the officers, Deborah, Diana, Willie, as well to the Paris Secretariat, Rosaria, Madeleine, and Lina, for their strenuous effort in coping with a difficult situation for an extended period. I accepted the officers' invitation to step in as ad interim to fill the General Secretary vacancy for the last 6 months, as it appeared to be a viable and quick technical solution. You will have a chance to judge where it was also a good solution during the business sessions. For now, I apologize for the delays in respecting the deadlines for distributing documents in preparation of the GA. It took me longer than expected to familiarize myself with the past documentation. We now have a solid, albeit challenging, financial plan for the next triennium, and with the support of the Secretariat and the officers, I hope I can clarify any question you may have about it. Finally, I thank Richard Green, who generously accepted my temporary replacement as director of the CPS, the Center for the Protection of Dark and Quiet Sky from the Interference of Satellite Constellations. Under his professional and wise direction, the Center continued to progress in its mission of safeguarding our science. You are invited to learn more about the CPS achievements by following its dedicated sessions. And I wish you all a very enjoyable and productive General Assembly. I'll come back later to present you several astronomy awards. Thank you. Come back here. And I invite the past president, Evin van Dishoek, to present the first set of awards for the Outreach, Development, and Education Awards. Evin.
Right, I also invite all the winners to come already on the stage here and stand here with me. So, dignitaries, dear colleagues and friends, both here in person, it's fantastic to see a full house, but also online. It's really wonderful to be here finally in Africa. We've looked forward to it for so many years, and now we are here. It's really a milestone. So this is a special part of the opening ceremony. The prizes for outreach, development, and education that were actually created in 2022. These prizes honor individuals or teams that have made really outstanding contributions in areas that are just as important to our field as research is, and that are actually at the center of the mission of the IAU. These prizes are actually awarded once every 3 years here at the General Assembly, so they are really special. If you look sort of at outreach, development, and education, you see that the initial letters actually form a word, and that word is ode. And that is actually very appropriate because you all know about odes. You know about the Ode to Joy from Ludwig van Beethoven. If you hear it, you can never get it out of your mind again. The Ode to the Nightingale, but there are many other odes. Odes to life, odes to earth. Actually, ode, set of praise. We heard about praise. Praise to our organizing team, to Kevin and his team for putting all of this together. But then also ode to our winners. So that is what we are doing here today. So a little bit about these awards, the eligibility, the description, the procedure for the prizes, they can be found on the wonderful IAU website, especially in the June 24 announcement of this year's winner. An important part is flexibility. Anybody is eligible, individuals, small groups, big teams, and they can be either for a lifetime achievement, but also for a major one-off. And they can be either globally or regionally. In 2022, we celebrated winners that made sustained impacts globally. This year, our winners, as you will see, are operating more regionally. My thanks actually go to the chairs of each of the three committees. For outreach, Komiko Sudasato, development, Solomon Tessema, and education, Brian Smith. These committees consisted of 3 to 4 members each across the globe. So let's actually go straight to the winners. And let's start with the O, for outreach. And the outreach prize goes to Saran Poshiachinda, who really put Thailand on the map in terms of astronomy and outreach. So Saran is actually a chemist with astronomy as a hobby. And personally, I can relate to that certainly a little bit. After some time abroad, Saran made the switch and back home established first NARIT, the important national institute, and several telescopes to go with that, not very least telescopes. But at the same time, immediately he realized the importance of outreach. He now has a huge team that reaches close to 1 million people annually through public observatories, an astropark, school events, and many more activities. He is truly fostering a culture of exploration and discovery among the general public in Thailand, but also beyond that in Southeast Asia. So here's the first award. Then the 2024 Development Prize actually goes to CENSA Bridge, the Central American Caribbean Bridge in Astrophysics. Let's go to the next one, which encourages and engages undergraduate students in research. These are students that have had very few opportunities before, but after the program, they successfully apply to graduate programs in STEM fields, not just in astronomy. Thus, astronomy is really used as a tool for capacity building, and it also symbolizes sort of the motto that we have: if you want to have astronomy for development, you also need to have development of astronomy. And that's exactly what is happening now in the Caribbean region. In their words, CENSA Bridge uplifts the region's astronomy research opportunities and showcases their unique strengths to the world. I'm particularly happy to see the younger generation represented among these prizes. We honor the founder and his team, Antonio Porras Valverde, Gloria Fonseca Alvarez, Valeria Hurtado, and Yahira Mendoza Mancado. There you are. And then finally, last but not least, the 2024 Education Prize, which goes to Linda Strube and Bonaventura Okeire. Together, they founded the Pan-African School for Emerging Astronomers, PASEA. Through this school, they have improved STEM education in Nigeria and Africa more broadly, using Okeire's vision to build on Africa's world-class astronomical facilities. Linda has brought in her strong teaching and evaluation experience, including the importance of teaching the teacher. The success is very notable, it's measurable, it's long-lasting among students. In this picture, actually, they look rather serious, but here you see them actually more in action. There they are, laughing and smiling and interacting with so many students. A big bravo to Linda and Bonaventure. And this then concludes the award ceremony. In fact, I just realized we have actually two of them. And then we have to another picture. So this concludes the ODI Prize Award ceremony. Please come to listen to all these winners. They are giving talks tomorrow here in this audience during lunchtime. We'll start at 12:15, and here you see the schedule also, the order in which they will be talking. So looking forward to see many of you again tomorrow. And again, congratulations to our winners.
So as announced, I will now go through a number of other awards that we are pleased to celebrate during this General Assembly. First of all, I want to mention the winners of the Gruber Fellowship 2024, Aldana Grichner from Israel, Jonathan Alexander Quirola Vasquez from Ecuador, and Honghui Liu from China. The certificates will be presented at the Gruber ceremony, which will take place on August 8 at between 12 and 1:30. So you're all invited to follow this presentation and their talks. These are very prestigious fellowships that, thanks to the Gruber generosity, we are giving to the most valuable young researchers. So it's one of the best program for sustaining the research of young astronomers. Then we have, thank you. Then we have the so-called PhD winners. This is a program that started in 2018, and each division is selecting the best PhD thesis in their area of expertise. And so we have here the list of the prize, the winners for 2023, which is for Division B, which is the Facility, Technology and Data Science, Jörgen Adener from the USA. Division C, Joanna Casado from Argentina. Division D, Jonathan Berry Ginat, Israel. Division E, Sun and Heliosphere, Robert Yarolin, Austria. Division F, Mohammad Farhat from France and Lebanon. And Division G for Stars and Stellar Physics, Roman Gerasimov from the USA. Division H, Charles Lowe from the USA. From Division J, Scott Lucchini from the USA. And there is a PhD at large prize, which is decided jointly by all the division presidents to go to Abril Saade, Argentina. And these certificates will be presented during the division days. You can see in the program when this will be. Then we have the prize winners for the year 2022. From Division A, Fundamental Astronomy, with Irene De Blasi, Italy. Division B, Joachim Moyens, the USA. Division D, Andrew Mummery, UK. Division E, Yai Chen, China, Nanjing. Division F, Malena Rice, USA. Division G, Antoine Bedard, Canada. Division H, Pius Schaarder, the Netherlands, and Division J, Daniel Orta Darrington, USA. Then we have the PhD at large, Naira Azetian, Armenia, and then an exceptional interdivision prize given to David Hosking, USA. And again, this will be presented during the division days. So later. Then we have also honorable mention. These are not the real prize, but you can see here the mention for 2023, Johannes Nassim Frederick Heil, UK, Andrea Silva Biscoveno, USA, the Division A, the Wojciech Kansabanek, India, Division A, Xingyu Zhu, China, Division F, Adina Feinstein, USA, Division F, Andres Izquierdo, the Netherlands, Division H, Elisa Rita Garro, Chile, and Division J, Amrut Alfred, Hong Kong. And again, this during the division days that will be even also mentioned. So thank all of them. And the honorable dimensions for 2022, Howding, Australia, Division B, Michael James Smith, UK, Division D, Alnes Pastor Marazuela, the Netherlands, Division A, Prabir Kumar Mitra, India, Division A, Yuto Becky, Germany, Division F, Tyler Gardner, UK, Division F, Misako Tatsunwa, Japan, and Division J, Kana Moribaki, Japan. Thank you, Bill. And now I invite the President, Deborah Elmer-Green, to proceed with the presentation on the following awards.
Thank you. Just to alert you to some of the highlights coming up in addition to all the focus meetings, symposia, and so on. I hope that many of you saw today the Shaw Prize laureates give a talk, Professor Matthew Bales, Professor Duncan Lorimer, and Professor Maura McLaughlin on fast radio bursts. Coming up on Thursday, Dr. Marsha Ricci will receive the Gruber Cosmology Prize, and we'll talk about the James Webb Space Telescope, 25 years in the making to discover the most distant galaxies. We'll have the Gruber Medal ceremony there and also honor our fellowship winners. Then we have on Tuesday, August the 13th, our Kavli Prize laureates, Professor David Charbonneau and Professor Sarah Seeger, and Dave will present a talk on the terrestrial worlds of other stars. You just heard about the ODE prize winners, and you heard from Aveen that their talk will be tomorrow here at 12 o'clock. Finally, we have invited discourse speakers. We have Dr. Bernie Feinarov, Professor Zhup She, and Professor Natalie Batalha, who will speak on Thursday, Friday, and next Tuesday here in the auditorium, all at 5:15. We have a number of public events with astronauts, Nobel laureates, all kinds of exciting people. So I hope you'll be able to take part in some of those activities too, really reaching out, bringing astronomy to everyone. So have a wonderful General Assembly. Thank you all, and we'll look forward to seeing you at the reception.
Congratulations to everybody. Well done. We are very nearly at the end. On the other side of the formalities will be a lovely reception with some snacks and beverages, South African style. We're going to wind things down with the man who's I connected with a good couple of weeks ago when I was interviewing him for a radio show that I do here in Cape Town. And he told me about this passion project, this vision that he had in his head. And that's how Radio Astro was born. He's going to close things off for us this evening. Before I invite him onto the stage, I do want to encourage you, while you are in my beautiful city, to do two things for me. To, when you post on social media, let your family and friends know about a wonderful time you're having here, and tell them about how magnificent Cape Town and South Africa is being to you. And the other thing I forgot to mention to you earlier about Radio Astro is that it is broadcasting free of charge to community radio stations all over the world. So please do go onto the IAU website, go and see how they can take that feed from us in your town every single day so that people in your community can hear what's happening in Cape Town absolutely free of charge. And the man behind all of this is the man who chairs the National Organizing Committee. I don't know how he does it. It is beyond me. I have worked with events coordinators, I have worked with events managers for decades. And they get very anxious, they get very nervous, they lose their minds at the end of it all. And I see this man respond to every single email and every single WhatsApp message, every single day for the last 24 million light years. He's extraordinary. He's been chairing the organizing committee, of which I've been part for the last couple of weeks. And like I said, I don't know how he does it, but I can learn a thing or two from Kevin Govender.
Come on, there's food waiting. You need to get on. All protocol observed. Let me, may you all allow me to say, we made it. We're here. It's finally here. It's finally here. So my job is to give thanks, but also to make some comments. And I'm going to break protocol a little bit and say, my first thanks go to you, because there is no meeting without people. And thank you, thank you, thank you for coming, for joining us in person and online. So this wouldn't have been possible without our host organization, the National Research Foundation, but with strong support, invaluable support from the Department of Science, Technology and Innovation. Of course, within the National Research Foundation, the facilities of the South African Astronomical Observatory and the South African Radio Astronomy Observatory were key players. And of course, the partner, through an agreement with the National Research Foundation, is the African Astronomical Society, which has been growing astronomy in Africa over the years. Let's give them a hand. This place costs money, right? It's a nice venue. Would you agree that it's a nice venue? It's a pretty nice venue. And we've needed sponsors, and sponsors not just for our costs, but also for travel support, because we had in this meeting over 1,400 grant applications, and I think it's a record for the IAU in terms of just number of grant applications. There's so many people across Africa, across the world, that want to attend this meeting, and we've had incredible support from our sponsors. The Simons Foundation provided a huge sponsorship for grants to support the attendance of the conference. We had the SKAO as our platinum sponsor, Brand South Africa as our gold sponsor, NAOJ as our silver sponsor. We had AIP, ESA, AWS as our bronze sponsors, and of course our prize sponsors, Kavli, Shaw, and Gruber, and sponsors for our Young Astronomers Lunch and Women in Astronomy, the National Academy of Sciences and the Norwegian Academy of Science and Letters. So let's give all of them a big hand. Thank you. I also want to thank all the exhibitors. I mean, there's some pretty cool exhibits out there, right? I mean, have you seen this exhibition area? Thank you so much to all our exhibitors. But really, the engine behind everything has been the National Organizing Committee, and we will recognize them fully at the end of this once they do their jobs. But they've been amazing, and they've actually got us here. But it's not just the National Organizing Committee. You see a number of volunteers around. Thank you for all the time you put in, and thank you for the time you're going to put in over the next 2 weeks. Our service providers as well, they've been amazing, providing the technical, the food, and so on. There's so many individuals, but it's not just the individuals. It's our partners, it's our families. And I think we have to acknowledge that we are all human beings. And as human beings, we all come with more than just our science. We come with our families, our friends. Each one of us has a circle around us. And in my circle in particular, I want to say a special thanks to Xavier and Cyprian, our kids, who have put up with me. Sure. They really put up with me. I promised them, after this General Assembly, I'll give them some time. But I especially want to thank, you know who I want to thank, my wife Carolina, because she's really the only reason I'm here. A meeting is about bringing people together. We are people first. But this particular GA is not just about bringing people together. It's about doing it with kindness and respect and humility and love. We are explorers. We are explorers for all of humanity. Our principle of making this open access, of the radio station, of the outreach, it's because we see ourselves as explorers on behalf of all of humanity, and it's important for all people to be able to share in this wonderful field of astronomy. We search for the existence of life, but do we search enough about what is the meaning of life? What can one achieve with one's life, and what should one's legacy be? If you look at this meeting as a life conceived in 2018, gestated for 6 years, and being born today, and then dying next week, what are we going to do with this life, this General Assembly? Are we going to walk away saying it was nice, with good memories, some new friends perhaps, maybe some souvenirs? Please visit our marketplace. No, we must walk away as champions for Africa. We must walk away knowing that we are going to make a difference, not just within this period, but beyond. The legacy of this event is super important, and that legacy starts with you. I compare to Carolina, and the minister was here. Last year, he awarded Carolina a posthumous award for science diplomacy. She was also the first recipient of the ODE prize. Many other things. And it's a legacy. She has a legacy that she has left. But more than that, the love that we shared carries me forever. And I carry a legacy, and Xavier and Cyprian carries a legacy in all we do. This GA is her legacy, because I wouldn't have done it without it. So to conclude, this is her wedding ring that stays with us all the time. But to conclude that analogy, let me say this: may we be the children of this IAU General Assembly. May we contribute to changing the view of Africa globally. May we create and enhance partnerships in Africa. May we see each other as equals, shaping the future of humanity together. It is time, my friends. It's time for respect. It's time for collaboration. It's time for exploring this universe together. It's time for kindness and love. It's time for Africa. Thank you.
What a fitting closing by the chairman of the National Organizing Committee, Kevin Govender. If as stars we begin, then as stars we return, sir. Isn't that wonderful? And I particularly regret not having met Carolina, but I've heard so much about her. So what a wonderful, wonderful tribute. Speaking of tributes, I don't know if a special song had ever been written for a General Assembly before. Has it? Not that you know of. Shall we just claim it? This is the first time in the history of the universe and all other galaxies and known universes that a song has been written for a peoples of that galaxy by an astronomer. This is the GA song for 2024, the 32nd for the IAU, written by an astronomer who's accompanying our choir, singing the GA song. A round of applause for Stephen Soti and his choir.
Akekho umuntu ongakwenza eyedwa kodwa sibumbene singakwazi.
Welcome to Africa. Ladies and gentlemen, I want to introduce to you a song, the GA song. If you're excited, give me a wave. Woo! Woo! So do this. Woo! Different, all astronomers in Africa. It's time to make history, yeah. Like the galaxies in Africa. Woo! Welcome. Go Africa, yeah. Africa. You wanna do this with me? Go, yeah. We can make a difference. All astronomers in our. It's time to make history, yeah. Like a galaxy in Africa. Hey. Welcome from all nations to the land of world. It's Africa. Go Africa. Go Africa. Woo. The sky is the witness of our story. Let us gather here together like the Milky Way. For your eyes and shine. Focus into situation. Searching for information we can use for. A better place. We can do this on astronomy. Let's come together. Yeah, let's come together. This is Africa. Africa, mtu mmoja haweza kufana ila kwa pamoja tunaweza. It's Africa. Bawanda Zaya Shikade Amatar Samboya. Yeah. It's Africa. Oh. Hey. Oh. Africa. 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 You want to join me? Oh, go Africa, Africa, Africa. Go, go Africa, Africa, Africa.
When Kevin told me that astronomers had other talents, I was like, no, surely not. There's a whole talent show. They do other things other than look through telescopes. Apparently they do. That's an astronomer, and I believe a star's just been born. I had to drop one. I had to drop one. There had to be one. I had a whole thing, but a star is born is very appropriate. We want to do something very special. We want to take a group photograph, which is why you all had to huddle. Or is it Hubble? No, it's huddle. Hubble. You all had to huddle a little bit closer to the center. So can I ask you to do that again for me very much, quickly? If you're sitting on the outer edges, I'm serious. I said this many times earlier. You need to move closer to the center because we've got not a wide angle lens. I was going to go somewhere else. It's not that wide, the angle lens here. So a little bit more to the center. Same on this side, please. I'm going to call the photographers onto the stage. The photograph's going to be taken from here, all right? And I'm going to ask you all to stand, but not just yet. First, we're going to get the photographer ready and get everybody to get a little bit more center. And stand is good, right? Stand is going to be good, I think. Your sitting is good for you. All right, all right. Apparently, we're doing it seated now. All right. We're going to do one serious, look how clever and academic I am photograph. And then we're going to do, I have also got other talents, look how fun I am photograph. Okay, serious one first. Photographer, it's over to you. Nicely done. That brings us to the end of the evening, folks. We're going to have one last bit of entertainment for you. This is very particular to Cape Town. We call them minstrels. We have a parade every year called Nuwejaar, New Year's, it's translated to. And there's a whole build-up through the months of December, or the month of December, a couple of days with lots of different troops compete against one another in the magic city, in the mother city. And then we have a final minstrel parade. And there's normally a troop that wins this parade. It's like a smaller version of Rio Carnival. It's the Cape Town version of it. And we've invited one of the top troops to come and lead you to the food. Are you ready to eat? So they're going to come on stage. What they're going to do is they're going to walk off the stage. You're going to follow them. And wherever they go, you go. Whatever they do, you do. Whatever they sing, you get the idea. All right. So they're going to come onto the stage. I'm Bobby Brown. I'm going to be at Radio Astro for the next 2 weeks. And I urge you to come and say hello. Here they are, folks. There you go, everybody. Go and dance for your supper. See you next time.